Okay, so we want to prove by contraposition that if 3 divides m squared, then 3 divides m. Remember, proof by contraposition is using the logical equivalence that P implies Q is logically equivalent to the negation of Q implies the negation of P. So if we can show that the negation of Q implies the negation of P, then that means the original statement P implies Q is true. So let's go ahead and start the proof. So we're going to assume the negation of Q, which is 3. We're going to assume 3 does not divide M. Okay? So if 3 does not divide M, this implies that M is equal to 3k plus 1, or M must be of the form 3k plus 2, where k is some integer, right? So we always will have to have a remainder, right? Because m doesn't, or 3 doesn't divide m, right? And these are the two forms that we get when 3 doesn't divide m. Because if we had 3k plus 3, right, we could factor out a 3, and then 3 definitely divides m. And if we had 3k plus 4, well, that's still the form 3k plus 1, right? So these are the two forms that we have when we know that 3 doesn't divide m. So let's go ahead and go to case 1. So let's have m is equal to 3k plus 1. Okay, so this implies that m squared is equal to 3k plus 1 squared, which is 3k plus 1 times 3k plus 1, which is 9k squared. So 3k times 3k is 9k squared. 3 times 1, or 3k times 1 is 3k. 1 times 3k, so that'll be 6k. And then 1 times 1 is 1. So this implies that m squared is equal to 9k squared plus 6k plus 1. And notice we can't completely factor out a 3 out of this, right? The best we can do is 3 times 3k squared plus 2k, right? But then we're going to have that 1 left over. So we can see that 3 doesn't divide m squared, right? Because it's of the form 3 times an integer plus 1. So there's a remainder of 1. So that means 3 does not divide m squared, right? So that means in this case, 3 does not divide m squared. Well, let's try the other case. Let's try the case where m is equal to 3k plus 2. So this implies that m squared is equal to 3k plus 2 squared, which is 3k plus 2 times 3k plus 2. 3k times 3k is 9k squared. 3k times 2 is 6k. 2 times 3k is 6k, so it'll be plus 12k. And then 2 times 2 is 4. All right, so let's see. We can rewrite this as m squared is equal to 9k squared plus 12k plus 3 plus 1, right? But I already know that I won't be able to factor out a 3 from every single term, right? I'll have, the best I can do is 3 times 3k squared plus 4k plus 1, but I'm going to have that plus 1 left over, right? So I have 3 times an integer plus 1 is equal to m squared. So this means 3 does not divide m squared in the case where m is equal to 3k plus 2 either. So in both cases, if we have that 3 doesn't divide m, then we know that 3 won't divide m squared. And that's what we wanted to prove. We know, so in all cases, right, 3 does not divide m squared. Thus, we've shown that if 3 does not divide m, right, if 3 does not divide m, then 3 does not divide m squared. So we've shown not q implies not p, so that means p implies q must be true. So thus, if 3 divides m squared, then 3 must divide m. And that is the proof.